In the early 2000s, 3G introduced an appealing concept: taking the internet with you. But the reality of actually using those early networks was often a test of patience. As millions of people bought their first smartphones, the system groaned under the weight of adoption. Trying to load a single web page meant staring at a stalled progress bar, and maintaining a consistent connection while in a moving vehicle was practically impossible. Consumers wanted to stream video and play live online games. The existing 3G infrastructure simply lacked the physical bandwidth to carry those heavy data loads through the air. To keep the mobile ecosystem growing, engineers realized that minor tweaks to existing networks would fail. They needed an entirely different method for wireless communication. Without a different way to handle data transmission, mobile devices would have struggled to move beyond text-heavy browsing and basic email, effectively capping the growth of high-bandwidth mobile software. That change arrived around 2010 with the rollout of the fourth generation of mobile communication systems, driven primarily by a global standard called long-term evolution, or LTE. The core of this upgrade was a complete structural overhaul. Network operators switched their entire backbone to an all-IP system. Older networks maintained separate physical systems, one for analog phone calls and another for internet data. 4G abandoned that split. It converted everything, including your voice calls, into universal digital data packets, traveling down a single consolidated pipeline. Routing all traffic as pure data allowed download rates to jump from single digits up to typical speeds of 10 to over 100 megabits per second. Standardizing every interaction as a uniform data packet allowed hardware to process information at scales that previous network designs could not reach. Creating a massive data pipeline presents a physics problem. How do you push all that digital information through the air at high speeds without the signals scrambling each other? Engineers solved this using a transmission technique called orthogonal frequency division multiplexing, or OFDM. Instead of trying to force one massive, fragile data stream from the tower to your phone, OFDM chops it up into dozens of smaller parallel subcarrier lanes. Spreading the transmission out mathematically avoids interference, making incredibly efficient use of the available radio spectrum. By acting as a highly precise traffic controller, OFDM ensures that complex files arrive on your device intact and at high speeds. While OFDM solved the software and signal logic, networks also needed physical hardware upgrades to handle larger volumes. This required a second major advancement: multiple input, multiple output, commonly known as MIMO. Previous generations relied on a single antenna. MIMO outfits both the cellular tower and the smartphone with multiple antennas, allowing them to send and receive separate streams of data at the exact same time. Because multiple streams are transmitting simultaneously, the overall data rate multiplies, and the connection becomes much more reliable, even in crowded environments. If OFDM organized the vehicles on the road, MIMO physically added entirely new lanes to the wireless highway. These invisible, highly technical upgrades created an entirely new foundation for software developers. Because 4G could reliably maintain a continuous connection, developers built applications based on constant real-time location tracking. This capability directly enabled ride-sharing services and launched the modern gig economy. Bandwidth-heavy tasks that previously required a hardwired desktop connection, like streaming high-definition video or joining a multi-person video conference, were suddenly possible from a moving train. With the bandwidth to support constant heavy data loads, the smartphone evolved into a central tool for managing daily life. But wireless infrastructure is constantly racing against human appetite. As global data consumption climbs, 4G is starting to hit its physical limits. The network struggles with extreme capacity challenges. Put tens of thousands of devices in a single dense location, like a stadium, and the resulting demand for simultaneous data can easily overwhelm a robust 4G tower. Furthermore, 4G struggles to provide the ultra-low latency needed for instantaneous machine reactions, and it isn't optimized to handle the billions of passive sensors required for large-scale Internet of Things networks. Just as 3G eventually bottlenecked the growth of mobile internet, 4G lacks the specialized capacity to handle an automated, densely connected future. To clear the next hurdle, network architecture needs to evolve once again.